All right, hello everyone. We're going to be going over section 9.2, which is on polar equations and graphs. So we have three objectives. For objective 1, we want to identify and graph polar equations by converting to rectangular equations. 2, test polar equations for symmetry. And 3, graph polar equations by plotting points. So starting off, just as rectangular coordinates can be plotted on a rectangular grid, polar coordinates can be plotted on a polar grid. Polar grids consist of concentric circles. This is circles within circles, and with centers at the pole and rays with their vertices at the poles. We use polar grids to plot polar equations. So here for our image A, here on the left, we have our rectangular grid. So it's what we're used to seeing. It's our XY plane. And for our second graph here, B, which is on the right, this is our polar grid. So we see we have these concentric circles here. See, we have these circles that are going around. If I can properly highlight them, there we go. And then we have these rays that are coming out from the pole. And these rays are representing different angle measurements. So these are our main differences with our polar equations versus our polar grids. With polar equations, we are essentially just making one full circle, and it's just all different values of theta going from 0 to 2 pi, very similar to the unit circle. Then we consider our distance or our ray to be the distance from the pole to whatever specified point that we do have. So that's how we define r and theta with polar coordinates as opposed to x and y with our rectangular grid. So the definition of a polar equation is an equation whose variables are polar coordinates is called a polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. So just our definition of a polar equation there. Objective 1, we want to identify and graph polar equations by converting to rectangular equations. So one method we could use to graph polar equations is going to be to convert the equation to rectangular coordinates. If our polar equation just gives us a value of r, something like r is equal to 3, r is equal to 6, anything along those lines, this just gives us the radius of a circle in the rectangular coordinate system. So if we see on our image here to the right, we're given this graph, we say r is equal to 3, which then, if r is equal to 3, that's going to correspond to the equation of a circle where we state that x squared plus y squared is equal to r squared. So if r squared is equal to 3, it's essentially just your radius for an equation of a unit circle, or the equation of a circle. So you would end up getting x squared plus y squared is equal to 9, which is 3 squared. So we know that often polar equations are given something like r is equal to something times cosine of theta, sine of theta, anything along those lines. This would be if you did not have a trigonometric function included. This would be if r was just equal to some number. Essentially what the graph of your polar coordinate would look like, it would just look like a circle with r being your radius of that circle. If our polar coordinate just gives us a value of theta, so no values of r in this case, just theta, where if we just state, graph the polar coordinate where theta is equal to pi over 4, pi over 6, etc. This gives us an angle at which we draw a ray going in both directions. So if you're just given a value of theta, that's just going to end up being a line. If you're just given a value of r, that's going to end up being the radius of a circle. So we have those differences there. When you do draw your straight line for your angle, you'll graph the line just as you would any other time. You want to find where that angle is on your polar coordinate system, draw out your line, and it goes in both directions at that point. Then from this, we can also get our theorem here, where if we let a be a real number, then the graph of the equation of r sine of theta is equal to a is a horizontal line. This means that it lies a units above the pole if a is greater than or equal to 0, and lies the absolute value of a units below the pole if a is less than 0. then the graph of the equation r cosine of theta is equal to a is going to be a vertical line. It lies a units to the right of the pole if a is greater than or equal to 0, and lies the absolute value of a units to the left of the pole if a is less than 0. So now we just have our two theorems stating basically what the equations of graphs of horizontal and vertical lines would end up looking like. If you want to see more examples in the book or more practice with things like horizontal lines or vertical lines, there are more examples in the book. I highly recommend you go and look at them if you want a little bit more practice with different types of problems. As far as timing goes, we're going to move on. So what we do want to do here is we want to solve example 1. So we're going to identify and graph the equation r is equal to negative sine of theta. So we have our polar coordinate system here. Let's zoom out a little bit. It's a little big. But we have our polar coordinate system in this case. We have theta from 0 to 2 pi. All of our theta measurements written out here, or the important ones kind of written out here. And we're going to graph this equation. So the first thing we want to do is, since in our objective here, we are taking polar coordinates, converting them over to rectangular coordinates, and then graphing them. So we want to turn our equation into a rectangular coordinate. Almost forgot that word there. So we're going to write in, we want to convert our polar equation to rectangular coordinates. To do this, we're going to multiply each side by r. We do this because if we multiply each side by r, we're going to end up with an r squared, which we know we can easily just replace with an x squared plus y squared. So we had r was equal to negative 2 sine of theta. This is now going to become r squared is equal to negative 2r sine of theta. We know we can replace r squared, so we're going to get x squared plus y squared is equal to negative 2r sine theta, where we know that r times sine of theta in this case is actually going to be equal to y. So what this means is that our equation is actually going to simplify to x squared plus y squared is equal to negative 2y. So we want to rewrite our equation because we want to write this in standard form. Standard form would look like the equation of a circle. So we have x squared plus y squared is equal to r squared. So we're going to add 2y to both sides, get rid of it. So now we're going to have a y squared plus 2y is equal to 0. And what we can do here is we can complete the square of y squared plus 2y. All we need to do is add whatever value would be at the end of that squared polynomial and then add that value to both sides. So the value that would end up allowing us to have a square if we had y squared plus 2y would have to be a plus 1 at the end of that value. So if we got y squared plus 2y plus 1, if we had to add 1 to both sides, and now we see that y squared plus 2y plus 1 actually simplifies down to just being y plus 1 squared. So we get x squared plus y plus 1 squared is equal to 1. So this is our equation in standard form of our rectangular, or this is our rectangular equation in standard form. But we want to put these in our rectangular coordinates. So this here, this is our standard equation of a circle with its center at what's going to be 0, -1. We see there's no change in x, but we do have a change of 1 in the negative direction for y. So the center of our circle is going to be at 0, -1. And this is in rectangular coordinates. I'm going to write coordinates as COORDS to shorten it up. And lastly, we identify that it's going to have a radius of 1. So, oops, forgot we made that smaller. So we've identified that this graph is going to be the graph of a circle. We have the equation of a circle, so we're going to be graphing a circle on our polar coordinates. We've already identified that the center is going to be at 0, -1. So our circles here are actually representing the values 1, 2, 3, 4, 5, and so on. So this first circle actually represents 1, the second represents 2, the third represents 3, and the last represents 4. So if we want to plot the point 0, -1, we would actually have to end up putting it. So our point would go right here on our polar coordinate system. This is the point that corresponds to 0, -1. And remember, this is our center, and our radius is 1. So this means that in order to draw our circle, the edges of our circle would be 1 up and 1 down. And now we just want to draw our circle as accurately as possible. So let's move our point out of the way here, move it over here. So drawing out our circle as best as we can, which is not all that great in my case, but you want to draw out your circle there. There we go. So basically we ended up with a small circle with radius 1 that was going to be centered at 0, -1. And this is the point on our polar coordinate that corresponds to the point 0, -1. But obviously this is going to end up corresponding with our radius and our value of r and our value of theta in terms of polar coordinates as well. You could check this with polar coordinates. We see that theta is equal to 3π/2. If we ended up, plugging that value into sine of theta multiplied by -2, we would end up with the same value of r that we had here as well. So, all right. From this example, we can also suppose that a is a positive real number. Then, if we have something that looks like positive or negative 2a sine of theta or positive or negative 2a cosine of theta, what we see that with our 2a sine of theta, our circle is going to have a radius a. So in all of these cases, the radius is always going to be a. Then your center, in accordance to 2a times sine of theta, your center is going to be at 0, a in rectangular coordinates. If you have a negative version, it would be 0, -a for sine of theta. If you had a negative version with cosine, it would then be -a, 0. Positive cosine, it would be a, 0. So just by reading this theorem, we can actually very quickly discover what our radius is going to be and where our center is going to be at. And then we determine that each circle then passes through the pole as well. So using these, it can be pretty straightforward to identify from our given polar equations what these would end up looking like in our rectangular coordinate system. So the method of converting a polar equation to an identifiable rectangular equation to obtain the graph is not always helpful and it's not always necessary. If it is very easy to do, then it can be very helpful. In some cases can be necessary, but a lot of times if your numbers are really messy, it's really not all that applicable. You can also just check for things like symmetry to try and cut down on the number of points that we need to draw out our graph. So relying on something like symmetry is that you would end up determining where your graph would end up being symmetric over things like the polar coordinate system. This would be, is it going to be symmetric over a certain line? Is it going to be symmetric over the pole or symmetric over the polar axis? Things like that. Once you know that it's going to be symmetric in some way, all you need to do is solve for certain points in one specific area, and then it's symmetric, say that it's going to look the same on the other side. But all right, objective 2, we're going to test polar equations for symmetry. So in polar coordinates, we say that r theta and r of negative theta are going to be symmetric with respect to the polar axis. Remember, this is our positive x-axis with accordance to our rectangular coordinate system. Points that are r comma theta and r comma pi minus theta, these are going to be symmetric with respect to the line theta is equal to pi over 2. In this case, the line pi over 2 just corresponds to the y-axis. Then we have an r theta and negative r theta are symmetric with respect to the pole or the origin. Another way we could test if it's going to be symmetric with respect to the pole or the origin. We can also test r comma theta and r of theta plus pi. So that's another way we could check. There are two different ways to check if it's symmetric with respect to the pole or the origin. So thinking of these, we have our three different images here. Graph A, we see points are symmetric with respect to the polar axis. So we're seeing this reflection over our polar axis, that positive x-axis part. For B, we see points symmetric with respect to the line theta is equal to pi over 2, which that line is just corresponding to our y-axis then in the rectangular coordinate system. So we see our reflection there as well. So you're really just seeing reflection around certain lines at this point. Then lastly, you have points symmetric with respect to the pole. So this is going to be really that opposite part of your polar coordinate system when it's symmetric with respect to the pole then. So thus we can get our three tests for symmetry. So one, you want to test for symmetry with respect to the polar axis. So for a polar equation, you can replace theta by negative theta. If an equivalent equation results, the graph is symmetric with respect to the polar axis. So that would be, if you plugged in negative theta into cosine of theta or cosine of any value, you plug in negative theta, it will give you back cosine of theta. So cosine, for example, would be something that would be symmetric about the polar axis. Then we have symmetry with respect to the line theta equal to pi over 2. So if you replace theta by pi minus theta, and if you get an equivalent equation, then your graph is symmetric about that line. Then lastly, symmetry with respect to the poles. So in a polar equation, replace r by negative r, or you can replace theta by theta plus pi. If an equivalent equation results, then you know that your graph is symmetric about the pole. These three tests for symmetry are sufficient conditions for symmetry, but they are not necessary conditions. So this means that a graph may fail these tests and still be symmetric to the polar axis, the line, theta is equal to pi over 2 or the pole. So if one of these tests comes out positive, then we know that for whatever test came out positive for, we know for a fact that it is going to be symmetric about that polar axis or the line. If we get that none of these tests come out conclusive, they say, well, they all fail, then it's just up for debate. It's not necessarily that it is not symmetric, it's just that we still don't know. So really when using these tests, it's either we're gonna know for sure or we're just gonna not really know. So there is no not knowing at all. There are a lot of no's there. So keeping those distinct is definitely going to be helpful.